Okay, today we are going to talk about systems of inequality. So, what we're going to learn today is how to sketch graphs of systems of equalities in two variables, how to solve systems of equalities, and how to use systems of equalities in two variables to, of course, model and solve real-life problems. So, first of all, let's talk about the graphs of inequalities. Now, any ordered pair is going to be a solution to an inequality if it creates a true statement when you substitute those x and y values into the inequality. Okay? Now, realize that inequalities have regions of solutions. So, inequalities in one dimension might have arrows on number lines, but in two dimensions we have regions of solutions that we show by shading. Okay, sketching the graph of an inequality in two variables. First, we want to sketch the graph of the equation, and you might need to solve for y if you've got a linear inequality, or if it's like a circle or a parabola or something like that. You might want to put it in other convenient forms that we've already studied so far this year. And then we're going to use a dashed line for greater than or less than signs, of course, and a solid line for the or equal to signs. And then to be able to determine where your shading is going to be, since some of these can get rather difficult. My linear tip is that you look and see where that line crosses the y-axis, and if it's greater than or equal to, you shade above that line, and if it's less than or equal to, shade below that line. Of course, if you're graphing from standard form versus slope-intercept form, you might want to do a test point just to make sure you're thinking properly. Okay? If you're graphing parabolas, you can use that same look at where it intercepts the y-axis technique. For things other than that, you're going to want to use a test point. And you might want to use a test point just to make sure anyways. So test one point at each of the regions formed by the graph. And by that we mean the greater or less than regions or intersecting regions if you have more than one inequality in your system. Okay, so that's what we mean when we say regions. So let's first look at this first system of inequalities. Our first one is x squared plus y squared is greater than 36. Now we can recognize that as a circle centered at the origin with a radius of 6. And when we zoom in on this graph, I've got them pre-graphed from Desmos, we can see it's centered at the origin, and we've got our circle. Now, we said greater than or equal to, okay? So again, we can use this intercepting the y-axis technique, okay? We see it intercepts it twice, up here and down here. But the greater than is going to actually end up being outside this region. So that test point, if you're unsure, what's the easy test point? Of course, 0, 0 is very, very hugely convenient. In fact, anything on one of the axes is a convenient test point if you want to check that out. Why? Because anytime one of your coordinates is 0, you have a lot easier time of figuring out things. Okay, the next one is negative 3x plus y is less than or equal to 10. Of course, if you wanted to put this in slope-intercept form, you'd get y is less than or equal to 3x plus 10. So you see a positive sloping line with a y-intercept of 10, and it's a less than or equal to, so we'll shade the bottom side of that. Now, this is what that graph looks like alone when we graph it, okay? Whoa, I'm losing my thing here. And then, last but not least, we have 2/3 x minus y is greater than or equal to positive 5. Putting that in slope-intercept form changes what it looks like. So we end up with y is less than or equal to 2/3 x minus 5 is what that ends up looking like. And here's what that looks like on the graph. And so we see that we have two less than or equal to's. Now, if we want to have our system, our true statement, be in all three of these regions, and we graph them all three, we can see where the regions are that they all three intersect. Now, in this area, there are no solutions. In this area, there's solutions for the circle. In this area, we have solutions for the first two equations. In this area here, we have solutions for the last two equations. But in this weirdly shaped area down here, in this area right here, we have solutions to all three equations. So this is where we can show that our solutions lie. Okay? Looking at another system, this is a system with no solutions. So we have our first equation still, that circle greater than or equal to 36, and here we have another one, this circle less than or equal to 1, okay? So we have radius of 1 centered at the origin, and our shading is inward. Now if we want something that meets both of these, this and this, then that's not going to be possible, okay? If it was an or, then we would have two sets of solutions, but if we're assuming an and, there are no solutions for this. So let's now talk about some applications. A store sells 2 models of computers. Because of the demand, they stock at least twice as many models of unit A, or X, as unit B. Okay? Oh, sorry. Unit A appears to be... No, unit A is X, and unit B is Y. Sorry. The cost of the store for the 2 models are $800 and $1,200 respectively, so 8X plus 12Y is less than or equal to 200. And that 200 is because we've essentially taken 2 decimal places off of everything to make our figures easier. We've scaled that down a bit, which we all know is perfectly legitimate. So we divided everything by 100, and 20,000 divided by 100 is 200, okay? Then management does not want to store more than 20,000 in computer inventory, and it wants at least 4 Model A's and 2 Model B's. So Model A's have to be greater than or equal to 4, Model B's have to be greater than or equal to 2. So we want to find a system of inequalities describing all possible inventory levels. So these first 4 graphs show these 4 equations separately. Now, when we zoom in to see the graph of all 4 of them, and keeping in mind what all of these look like, so we've got some greater thans, we've got some less thans, and we've got some other greater thans, we can see, and I'm going to draw this actually in white, that this triangle here is where we need to keep our inventory levels. So we need to have at least 4 and 2, respectively, of A and B, and we can see that here, 4 and 2. And if we have 5 A's, we still only want 2, or maybe 3 B's, okay? And so that keeps going up. So the max that we will have of either set is, or both, if we maxed out both A's and B's, we would have 14 A's and it looks like 7 B's. Okay, if we optimized how many of both that we could keep in stock. If we minimize everything, we could keep at least 4 and 2. If we maximize the amount of A's, we would have 2 B's and looks like 22 A's. If we maximize both, that happens at this vertex. So you can see, you can learn a lot from systems of inequalities, and of course all these different possibilities in this region also exist. But we can learn a lot about a business from just simple inequalities and deciding, hey, this is what I need to do, and it could apply to any number of different decisions that we have. Okay? So, we've learned how to sketch graphs of inequalities in 2 variables. We've learned to solve systems of inequalities. We've learned to use systems of inequalities in 2 variables to model and solve real-life problems. And that's it for today.